Welcome. Thank you so much for joining us today. That we are going to have a wonderful webinar on developing conceptual models for implementing integrated water resources management. And our presenter today is Jerry Selke. We're going to talk about Jerry in just a minute. So let's talk a little bit. Here he is right here, and he's connecting with us from where are you at, Jerry?
From Savannah, Washington, in Washington State.
Oh, great. Is that where you're calling in from, or are you in Idaho today? Super.
Nope, I'm in Washington today. Thanks.
Great. Thanks so much for being here. Jerry's a past president of the American Water Resources Association. We're actually absolutely thrilled that he's here today. I'm Lisa Butler. I'll be just moderating this session, and I am filling in for this guy, Michael Campana. He is the technical director and past president of the American Water Resources Association, and I happen to be the president this year, so we've got a couple of presidential sorts on the phone and working on this webinar today. So we'd like you to know that ARA is scheduling webinars for 2019 and 2020, and we'd love to hear from you as to what you might like to hear about. If you have a speaker you'd like to suggest, including yourself, just let us know, get us the contact information and why you think the topic is important. And just drop any of us a note. I'm president at ara.org, or you can call, or you can drop a note to Dr. Campana at aquadoc@ara.org. We also have a lot of very cool things coming up. We've got a webinar on catchment carbon offsets trial. This is a case study, and our presenter will be joining us from Australia. So we've adjusted the time just a bit so that he didn't have to get up in the middle of the night. We're going to be up in Reno at the specialty conference on improving water infrastructure through resilient adaptation. We're very excited about this. There's still time to register for this, and I think you can get some pretty good room rates in Reno in June. So I'm going to strongly recommend, if you're interested in this topic, that you take a look at this particular conference. And we are also planning to head to Beijing in September. Again, registrations are still open for this. This should be a pretty amazing discussion. We're going to be talking about water security. We want to thank you for participating in this webinar, and I'm going to be turning this over to Jerry. And Jerry, you ready to roll?
I'm ready to roll. Thanks.
Okay, very good. Take it away.
Okay.
Perfect.
Well, good afternoon, everyone.
Right now we see your screen instead of your PowerPoint. There you go.
Okay, as Lisa mentioned, my name is Jerry Selke, and I'm going to talk about developing conceptual models for implementing IWRM. So let's get right to it. So first, I guess most people are probably familiar with IWRM, but there may be some on the line that aren't familiar with it. So let's start off with the definition of what IWRM is. The most commonly used definition was the definition coined by the Global Water Partnership in 2000. And that's IWRM is a process which promotes the coordinated development and management of water, land, and related resources in order to maximize the resultant economic and social welfare in an equitable way, or in an equitable manner without compromising the sustainability of vital ecosystems. So that's the big picture of what the community thinks that IWRM is in general. So the American Water Resources Association board developed a policy on IWRM. AWRA is a believer in the process and the potential benefits that can be gained from IWRM. And so they developed a board policy, and that policy is AWRA recommends that water management policy goals, programs, and plans be organized around the concept of IWRM, the coordinated planning, development, protection, and management of water, land, and related resources in a manner that fosters sustainable economic activity, improves sustains environmental quality, ensures public health and safety, and provides the sustainability for community ecosystems. So it's a long way of saying, we want an integrated approach to managing the resources and to doing it for the right reasons in a manner that fosters sustainability. And so I'd recommend that essentially that we implement this in planning and managing on really all scales, on the national, international, interstate, and local levels. So, so AWRA as an organization is bought into the concept that we should be trying to practice integrated water resources management. Well, what we have bought into it, not everyone has, because some believe that there's some problems with integrated water resources management. Biswas is probably one of the key people who has critiqued fairly heavily integrated water resources management. And what I like about it is he didn't just complain it's too hard or too tough or too vague or whatever. He actually took the time to actually dissect IWRM and come up with some ideas of what's wrong and what we need to be thinking about. So that's valuable. A little critique is always a valuable thing if given right and if accepted right. So his major criticism, or one of his major criticisms, is that the IWRM is the goals are overly broad and the language is too vague. It's so when we think of it, we heard the definition that was given, and it's it's this high level thing. It's about integration and integrating resources and so it's a big picture thing, and how do you take that and bring that down to something that's implementable? So he points out in one of his papers that, in fact, if you take all of the things that different people have been saying about integrated water resources management, that each program would have to have about 41 different goals to achieve what is IWRM. And his suggestion is that's too broad and it's too complex, and you can't essentially cover all of those things in all cases, and so it's problematic. And there's there could be some truth to that. We need to be careful. We need to constrain, put some sidewalls on things, and make it so things are understandable and implementable. Excuse me. So the American Water Resources Association in 2012, its policy committee published a case study called a Case Study in Integrated Water Resources Management from Local Stewardship to National Visions. And this study is available. If you Google that, you'll be able to pull it right up off the internet, and you can take a look at it. And I highly recommend people do to take a look at this case study around the United States. Because what the study did was it took 7 water resources projects in the U.S. that were broadly distributed and very different in their base and their basis, and it looked at what are the our IWRM and our IWRM-like principles and theories, and how do they get implemented within these programs. So if we look, here's the map of the studies, and what we have up here in the upper left corner is the Yakima Basin in Washington, the state of Oregon, the state of California. Down in New Mexico, we have the Rio Grande, the Upper Rio Grande. In Minnesota, we've got the Minnesota Basin. We have the Delaware Basin, and we have St. John's Basin in Florida. So these are quite different. Of course, Oregon and California are statewide, very large. We have the Delaware and the Minnesota, which were pretty big projects. And then we have the smaller projects in Yakima and the Rio Grande and St. John's. So what it does is it provides us with a whole plethora of things to look at, everything from size, physical footprint, to complexity and the number of people and the number of issues and such. So there's a very broad scope here to look through and to see how things work. So the results of the case studies, I guess, number one is that each of the studies showed some aspects of IWRM, but none of them really implemented all of the aspects that I would have expected to see in a comprehensive IWRM project. So each one provides some aspect and I guess, focused on certain aspects, and then other ones picked up other areas. So the study, when we look at the results, what the study tells us in part is that that IWRM, what we've seen is that it's hindered by the lack of a consistent definition that can be made operational and measurable with measurable criteria. So that's pretty key. You know, we need to be able to have something that says this is what we're doing, and we can actually implement it, and that we can actually measure the results and say, yes, the IWRM has been successfully implemented or not. And that's difficult, but we need to try to do that. What they saw also is that real life political, social, and physical factors made it difficult to implement IWRM in a number of cases. So we need to look and see how can we better work on those issues in our basin or our hydrologic unit that we're dealing with. And it also stated that more focus is needed to refine IWRM concepts to research and quantify results. So that's exactly what we were doing here is in this case study was looking at a bunch of studies that were IWRM intended or they were IWRM-like, and look and see how they do, how they fare, what worked, what didn't. That's how we'll learn. And there's a number of studies internationally also that have done this, that has taken a retrospective look and said how did things work and what can we improve. I think that's really important. So the question is, how can we better design IWRM if we're having a hard time taking the definition and actually implementing it, measuring it? How can we make it better? Well, Biswas and others keep saying, or have said, that what we need to do is redefine. We've got to come up with a new definition of what IWRM is. But I think the reality is that we can't develop a definition that both gives us more specificity, but also gives us the flexibility we need to be able to address the issues that we need to address over a really wide range of different hydrologic units. So what we need really is to develop a better conceptual model. That would be my thesis. We need to develop a better conceptual model of what we think IWRM is. Not try to just define everything into it, but to look and say conceptually, what do we need? So we need to develop a conceptual model of what a baseline IWRM program should contain and what it should look like on the ground. And we need to build conceptual models that are flexible enough to recognize and be incorporated in different areas on the local, regional, or national levels to meet those needs, and to take advantage of the opportunities and to be able to address some of the constraints. So in the bottom line is we need to be able to implement it at various scales and various watersheds and basins. So that requires flexibility rather than trying to get more exacting on the definition. So let's take a look at that. So conceptual models are needed to help us better visualize, plan, and monitor and manage hydrologically connected or interconnected waters and their related resources. And we needed to be able to work with being able to bring together the data and information we need to do that. The conceptual model should be designed to help stimulate those who are working within these basins, be they decision makers, managers, researchers, or water users, whoever, to better understand, manage, and govern our water resources. And you know, we can't fool ourselves into thinking that just because we came up with IWRM, that this is our first shot at trying to manage these well. We've been managing both the studies and the implementation of programs pretty well overall. But we need to be able to do it in a more holistic, systematic, integrated manner, I think. So that's really what we want. We want a model that makes people look and say, okay, I see kind of the basics, but maybe this doesn't fit for me. Maybe I need to make some adjustments, or maybe I have some other things I need to add in here and adjust my studies or my programs to meet those specific needs that I have. So we're trying to stimulate people to think is what we're trying to do, in large part with this conceptual model. So and what we need to do is include all of the basin's specific information we need. We need to have the basin-specific hydrologic cycle information and factors that impact or can be impacted by the cycle. We need to know the full suite of human and environmental needs and the activities and impacts and their interrelationships with each other. And we need to do that depending on what basin we're in. We'll need to do those things at different levels. And what we need to do is make sure that we have this bigger picture understanding, that that's part of it, but that we can take all that information that we actually need and that we actually have the information for in order to meet our goals. So we need to do this kind of or gather this information to the extent we can and to the extent it's needed to meet our goals for understanding and managing our unit of interest. So how do we do that? Well, all of us do conceptual models, I think, in our minds. And from our thinking through our process, we often write them down on the blackboard or write them down on paper, or we type them up, or we put them in models. Personally, I do a lot of systems dynamics models, trying to look at, build conceptual models and look at them. But in general, we have a similar process. We review the available data and information, and we then conduct an assessment of the area of interest, and we collect new data and information. And we learn from stakeholders. We find out about what do they use water for, what do they need, where are they at, what's their footprint, just all kinds of information that we need from them. And then we evaluate water user competition and cooperation. And this may be an extra step that most people don't emphasize, but I tend to emphasize it, because really what we want to know often when we do these studies is we have competition between water users, and what we want to know is what that competition is and how can we help alleviate it and how can we increase cooperation. So I just put this in as an aspect for me. I want to know specifically what's helping, what's hurting, and where the problems are, and whether we can find some better cooperation and coordination. So then we compile both the anthropogenic, the human needs, and the environmental needs, see what they all are, and we formulate our questions that need to be answered by our studies, or things that need to be implemented. And then we note data and information gaps when we're doing studies and say, do we have enough information to do what we think we need to do? Well, if we do have enough information and data, then we can just move on and continue on with our study and implementation. If not, we just start the cycle over again, do another review of the available data and information, and go through the process until we have sufficient amount of information. So relative to integrated water resources management conceptual models, essentially we use the same process. They're developed in a similar manner, except for what we need to do is we need to be broader in nature and more integrative in the way we manage things. So we need to be broader in that we need to understand the bigger picture, and I can't emphasize this enough. We need to understand the overall big picture, even often bigger than where we're doing our study or where we're doing our implementation. So we understand what's affecting us and what we're doing, and what we're affecting outside of us with doing what we're doing. So we need to be broader and more integrative. We need to integrate our knowledge of the hydrologic, physical, social, economic, legal, and environmental aspects and issues within the area of interest more fully than historical management approaches. And again, I would say we've been doing studies for a lot of years. We've been working at these are not new pieces, but what we're trying to do is to look at them more fully and to exercise them, to manage them in a more systematic and integrated manner than historically. And this is a little bit different than that we've maybe thought of it in the past, but I think that in my opinion, all IWRM programs should be conducted, they should be designed and implemented, conducted within a competent hydrologic unit. And that may be a basin. We'll use the basin as the example. But let me discuss that just a little bit further. So for a competent hydrologic unit, if we look at Agenda 21, it states that integrated water resources management, including the integration of land and water-related aspects, should be carried out to the level of a catchment basin or subbasin. Well, when most people think of especially a catchment or a subbasin, we tend to think of surface water only. And what I would argue is that we can't just deal with surface water when we're talking about integrated water resources management. Again, it's my opinion, and it may be in some areas we do our studies that we don't look at the whole big picture, but I would argue that if we're doing integrated water resources management, we have to look at every compartment, every hydrologic compartment, be it atmosphere, surface water, groundwater. And the reason is how can we run an integrated program if we don't know the other pieces? Now, it may be that in doing so, we don't actually do a whole lot of work on all three components, the atmosphere, surface, and groundwater. We may concentrate on the area that's really of interest, which may be surface water, groundwater, whatever, but we need to understand all three. And so what I would say is in order to do that, we need to have competent hydrologic units, which I'm defining here as the full geographic extent of a hydrologically distinct surface water unit and its hydrologically distinct and interconnected ground water unit within a specified geographic area of interest. And so what I mean by that is if we have a small watershed over a large aquifer, then the aquifer would be the footprint that we should look at, because the watershed we're working with, whatever we do there, is impacted by what may be coming up to the watershed from the groundwater, upwelling maybe, or discharges to streams, or what we do in our watershed may, discharge down to the aquifer, so it may affect it. And actually down the line or up gradient or down gradient, others doing the same thing may be impacting us. So we need to look at that full unit. Now, it may be that, again, that we don't do in-depth studies because maybe that's outside the scope of our work, but we need to consider that entire footprint and what things may be affecting us and what we may be affecting as we're studying and as we're implementing our programs. So here's an example, competent hydrologic units in the Upper Snake River Basin in Idaho. This is where I've done most of my work for much of my career. And if we look up here in the upper left-hand corner, what we have is, this is the Idaho National Laboratory, which is where I was employed for most of my career. And what we have is the Upper Snake River Basin. So this is the entire surface water unit of the Upper Snake River Basin. Now, this information was gained from the U.S. Geological Survey GIS information that's available readily over the internet. And this was, I believe, at a Huck 8 level that we're showing here. Now, if we look down below on the lower right, we have aquifers. And so these, again, they're within the Upper Snake River Basin, okay? And what we have is, if we look, we have essentially 13 aquifers that feed in, that are tributary to the Snake Plain Aquifer, which is the main aquifer in eastern Idaho. And if we think about it, so what happens up here in the Big Lost River watershed impacts two aquifers, the Copper River, or the Copper Basin Aquifer and the Big Lost River Aquifer, and those impact what happens in the Snake River Plain. It's actually the Big Lost is the largest tributary water-wise to the aquifer from within the basin. So what we need to do is then take a look and say, if I'm looking at the Big Lost River, I need to look at both the surface water and the groundwater portion. So that would be the watershed or catchment and the aquifer. But we also need to look and say, what we know is that those waters come out into the Snake River Plain and affect people in the Snake River Plain aquifer and the environment and other aspects of this. So we need to look at, again, at that bigger picture. And if we're looking at the entire basin for some reason, like when we did for adjudication purposes, then we need to consider each of these in detail. But whether it's part of it in detail and the others in the bigger picture, if you look at the whole thing as the big picture and do it in detail, just depends on the scope of the work you're doing. So again, this is just to emphasize the fact. So here what we have is climate-related things, we have surface water-related things, we have groundwater-related things, and so aquifers, hydrologic units, and the atmospherics. And so whatever level we're looking in here, whether it be at the national, regional, local scale, whatever, what we need to do is say, what is connected? What is connected to this? What is in, besides my little area that I'm working on or my big area I'm working on, what other things are connected to that hydrologically? And the same thing goes for, if we look on the right-hand side, when we're talking about the social, economic, and environmental and other aspects. In this case, what we're showing is governance. And so we have the federal government that has primacy over certain laws and regulations. We have state primacy over certain laws and regulations, and we have local. So an example for federal would be water quality is governed at the federal level in the United States. So what we have is the federal's in charge. But when we talk about water rights in the United States, that's a state function, and so the state has primacy. But they both impact each other, right? So that if we're working, let's say, at a local level, if we ignored the federal and the state laws, we could have ourselves a real problem. And if we're working at the state level, we have to consider what the local is. The state may have primacy over the local, but the local has local interests and knowledge and such, and we need to have that incorporated. And the same thing with tribal, when we're talking about Indian reservations and such. We need to be able to look at each of these and say, I am concerned here or here, but what are the other aspects that influence my understanding and my implementation of IWRM? So here's kind of the big picture schematic of what I believe to be a comprehensive look at integrated water resources management. And so what we have is we have hydrologic inputs and outputs, standard for every hydrologic study done. You got to know what's coming in, what's going out of my unit of interest, my competent hydrologic unit. We have physical constraints that impact whether water's usable. We have social economic constraints, which can also impact what is actually usable. We have legal constraints, and we have environmental constraints. So all of these are different constraints. There may be enough water in the basin physically, but there may be other constraints that say you can't use it. Now we have all the water uses over here that are associated, or that these are all common in the United States, common beneficial uses we call them in the United States. And we have various ways of how we get that water. So we take available water and we capture it somehow, we put it to use, and then it can be used consumptively or non-consumptively. So let's break this down a little bit more, and let's take a look and see what each of these parts tell us and see how they make sense together. So basin inputs and outputs, as I mentioned, we have groundwater inflows and surface water inflows. We have precipitation coming down. Some of that precipitation will just evaporate or be transpired and leave the basin. We have some that makes it down to the surface and stays in the basin. We have surface water and groundwater outflows. We have evapotranspiration losses from a basin. And then we also got to remember, we've seen in a number of places that there are major water transfers between basins, and there's potentially virtual water exports. When you export a lot of foodstuffs, you may be exporting a lot of water along with it. So this, again, is up here in this area of hydrologic inputs and outputs. So if we have just a single small watershed, then what we're looking at is essentially we would have an atmospheric water source, and it would go into a watershed, and that could be surface water, it could be vadose water, it could be groundwater. And each of those interact within that watershed and between the atmosphere and that competent hydrologic unit. So we need to look and understand if there's a specific answer we're trying to get to or trying to manage it, and we need to look within that one and say, okay, what's the ET and what's the precipitation and how is that moving between surface water and vadose and groundwater? And then if we're in a larger basin, we'll usually have multiple watersheds or multiple catchments, multiple competent hydrologic units in my terminology. And so it may be that there's 3 of these or 4 or 5. It could be that we need to look and say, what is their interaction between them? Okay. So we have physical constraints, and how I define physical constraints is temporal distribution, spatial distribution, quantity, and quality. And essentially in most water resources analyses and management, these are the 4 things that we need to understand and or control or utilize in order to say we can have a sustainable resource to use, right? We need to know where it's at in time and space. If it doesn't come at the right time, then we do things like building reservoirs. If it doesn't show up in the right location, we may build reservoirs and then pipe it somewhere or divert it somewhere. Quantity is obvious. If we don't get enough rain, then we don't have water on crops, and then we have to find supplemental. And quality, to me, is a key aspect that's obvious to most of us, but often is considered to be separate from water allocation. And I would like to dispel that and say we always, when we're thinking about water availability, always should consider water quality. So let's just talk about it just for a minute. Physical constraints, depending on the seasonal annual precipitation and the surface water, groundwater flow patterns, water may not be available where it's needed and in sufficient quantities to meet all of its needs for human or for environmental purposes. And so, again, as I mentioned, if we don't meet these needs, then we, as managers of water, then have to figure out what do we do to accommodate getting it to the right place at the right time in the right quantity. But again, water quality in the United States, I don't know how it's managed in other countries, but in the United States, water quality and water quantity have historically been managed separately. And in many, many states and other locales or locales within those states, they are managed by different agencies, and they're managed differently. And in some cases, we intentionally ignore the quality aspects out of fear that it may impact quantity aspects and the ability to allocate water. I would say water quality should always be integrated, because if the water is not sufficient for the uses that we need it for, then it's essentially not available, right? So water would not be available because it's too dirty or too contaminated to drink. And that may be remedied. You could remedy that through treatment if you can afford it, if there's actually a remedy for it. But it always should be considered as part of that four-part water location, timing, quantity, and quality when we're talking about managing water. So these factors, each of these factors can make water available in some areas and not available in others, and that is water managers. That's what we're paid to do, is to try to take that where we have those disparities and make it so it's available where we need it, when we need it, for the purposes we need it. So let's look at some of the other constraints that, we often think about these, but somewhat separate, or often it's probably we think about them, but we don't think about it wholly. We don't think about it up front as well as we should sometimes. And we don't think of them so systematically. And social, let's start with social economic, and then we'll work down through legal and environmental constraints. So social issues such as community preference and historical practices and norms. and various community and political issues that are going on within a competent hydrologic unit can greatly affect what is going to happen within a basin. It's going to tell us whether we can develop some water, or whether we can protect some water, or whether we cannot develop or protect water. It just depends on what it is your goal is. We're trying to understand the basin and trying to implement something. If you're pro-development and somebody comes up and says, I just don't like you messing with my water, we tend to say, well, that's too bad. But if you get a few thousand people saying that, pretty soon you may find you're not going to develop, because social pressures may, no matter what the other legal or physical things say it's okay, social pressure may say, no, you cannot develop. And in other places, it may say you can't protect the environment. We're going to totally develop. There's places in the West, in fact, where we have the right to totally drain streams dry. And because of the water rights, the way it's set up in the community norms is that human use is more important than environmental use. So we just ban, we don't ban, but we do not protect those resources. So social issues are really, really important. We need to keep those in mind. Public acceptance and buy-in is just vitally important for shaping the development of and management of the water resource. So keep those in mind. They're really, really important. Legal constraints. In the United States, we have a plethora of legal instruments out there. We have them at local, state, and federal levels. We have water quality issues, water quality laws and policies. We have water appropriation policies and laws. We have treaties. We have compacts. We have environmental laws that impact. We have treaties with Native American tribes and Indian reservations. So we have a plethora of things that could either help enhance getting things done, or to impact getting, or to prevent us from getting things done, depending on what it is we're trying to do where. So generally, these legal instruments have been developed with the intent of providing some semblance of predictability and control of the water and water-related resources. Often we hear that people say, oh, the law always gets in the way, but I would say in most places where water is being run well, that means that there is a good set of legal instruments in place that actually help us get these things, get the things protected that need to be protected, that allow us to develop what we want to develop, and when it makes sense. So legal constraints, they can constrain things, but that is not always a bad thing. So that is a really important aspect of water development, water protection. And the same thing with the other resources we're talking about, the protection or the use, maybe the harvest of environmental or ecosystem services. So those are really, really important to know. And in the United States, we're in good shape with that. Some other countries maybe not so well. Maybe they don't have sufficient legal instruments in place. Environmental constraints can be interpreted in a couple ways. One is just the actual physical aspect of what we're going to do or what we're going to prevent relative to physically harming either an ecosystem or a species or a population of, could be plants or animals or whatever. The ecosystem services, we want to use our natural resources, be they land, be they animals, be they plants or whatever. Those are valuable to us, but there's also a certain amount of protection that's required to protect them, both for our use, to make sure they're sustainable for our use, but also for just the innate protection of a resource. We shouldn't be trying to denude the world of our ecosystems just for economic benefit. So they can be thought of as a point of where we may threaten the cherished ecosystem or population. So that's one way of looking at it. There's also just the environmental aspect where we have laws in place to protect various environmental aspects. And just from a regulatory standpoint, we may cross a line where we can no longer develop the resource that we may be limited or curtailed in what we're trying to do because we are not meeting the letter of the law or the requirements of the policy. Either way, whether you're talking a real or a legal, and I say in quotes, real or legal or policy constraint, the truth is they all stop projects from happening, or they can cause things to happen. So we need to keep that in mind. So water acquisition and use. So we have water that comes into a basin, that stays in, becomes useful as fresh water. And we have different ways of capturing that. So we have rainwater harvesting, bringing water straight out of the atmosphere and harvesting it, and typically using it for domestic use. We have surface water diversions, where we divert streams and ponds and swamps and whatever, hopefully in a very responsible manner. And those can be used in various uses for ag or domestic or commercial, municipal and such. We also have groundwater that can be used for multiple uses. And then we have in-stream flows that just come through and flow through and help with the ecosystem services and typically things like navigation. In a few cases, it could be commercial. Back in the days when we had mills that were physically moved by water. And this is not as common now in most places, but still out there, I'm sure. And then we have seawater pumping, where we take water actually out of the ocean and we may desalinize it and use it for various uses, or we may use it straight for cooling and energy production processes. And each of those are either consumptively, the water's either consumptively used or it's non-consumptively used. If it's not consumptively used, then essentially you have return flows that can go back into the system. Maybe it returns to the surface water, to the stream or river or whatever you're using, or maybe it goes down into the aquifer. Maybe we run it down an injection well, or it seeps into the ground and it recharges, and then essentially it's available for use further downstream. So we need to know these various aspects. What water is available, where do we get it, what do we use it for, and whether it's consumptively used or not, and how does it come back into the system or not for further use. So then the idea is to bring all these back together. You take all these parts and pieces and put them back together and say, looking at the whole picture, this is the kind of thing that I need to know in order to implement IWRM in a hydrologic unit, in a comprehensive hydrologic unit. So that's kind of the big picture look of going through there. So let me give a couple examples of some things that we've done along these lines, looking at this bigger integrated picture. So as I mentioned before, we have the surface water basin up here in Eastern Snake River Plain, the Snake River Plain. We have the aquifer systems here that they connect. And what we can see over here on the right is the state of Idaho has a system for categorizing, for numbering and naming and categorizing their aquifers. And so as I mentioned earlier, the main one in my part of the world is the Snake River Plain. That's here. And if we look here, what we have essentially 21 surface water units that sit over this aquifer or contribute to the aquifer. Okay? And so these are the names and the numbers for the hydrologic units that overlap this aquifer here. And then we have other aquifers out there that overlap by other watersheds. And in some cases, a aquifer may be under multiple watersheds, or multiple watersheds could be over a single aquifer. So it just depends on the system. And so we look at those. We use this especially when we were putting together our Snake River Basin adjudication, looking at who's connected to who relative to surface water to groundwater, watersheds or hydrologic units to aquifers. And those that were connected are mandated to be adjudicated together and to be managed together under our state law. In the Big Lost River, again, here's the Idaho National Laboratory. We used this diagram and this information for a couple of studies we did relative to source water assessments for our drinking water system. Everything of upgradient of us, be it surface water or groundwater, comes down into the INL and it affects water that's recharged to our wells. And so it could bring contamination and it brings water down to our systems. So we needed to look, and if we take a look, this is at what's called a HUC 12 level, hydrologic unit 12 level. So very small sub-basin. Because both for the source of contamination, we wanted to be able to isolate those sources and look at them closely. And then from flood assessment standpoint, we use that to look at specifically because of the large elevation difference between different watersheds. This is a very mountainous area, and we need to know relative to melting of water how it would come off in a flood flow. So this caused us to look very closely at this basin, at the surface water, the groundwater, at who's using what water, at who's potentially contaminating the water and such. So again, a very integrated approach to try to understand this basin and its impact on Idaho National Laboratory. Here's another study we did down in the Bear River Basin, and this is a case where we have 3 states, Idaho, Utah, and Wyoming. They share the water from the Bear River Basin, and water starts down here in the south and works up and crosses 4 or 5 times, crosses state boundaries and then up through Idaho and then crosses again down into Utah. And every time this river crosses a boundary, then by Western water law, or at least how it's implemented up here in the basin, every time it crosses a state boundary, it becomes a new river. Well, we know that the river that starts at the top goes to the bottom, but from a legal standpoint, every time it crosses, it becomes a new reach that is managed independently historically. And so what we wanted to do is take a look at that big picture and say, how do we actually really manage water? So we integrated the information on the aquifers, we entered the information on the river, on the dam systems. We looked at the Barrow Lake, which is the governing body of water. It's what controls flow downstream from storage. And we looked at all the aspects of water use and such water rights. Okay. And what we did then was trying to pull together in an integrated way, how can we look at what's there and what's being used and what the impacts are, and how would that be managed under the Bear River Compact, which will decide who gets what water in times of shortage. So this is just another example of things we looked at and tried to look at it from an integrated water resources management perspective. Finally, here's an example of a study we did in the western United States. So we could do this on a very large scale, just like we can do it on the smaller scales. Of course, the granularity is a little less, or maybe a lot less. But essentially what we did was we took U.S. Geological Survey HUC maps, the watershed maps, and we combined it with the USGS's aquifer maps and on GIS. And what we developed was essentially these competent hydrologic units. We were able to look at each watershed at or HUC at a HUC 8 level, 8 unit level, and we overlapped that with the aquifer information that was available and looked at how the surface water unit and the groundwater units integrated with each other. And we built this map in which we did analysis to look and say what water is available, what's being used, and how in the future, how much water in the future may be available under given scenarios for getting water for essentially for generating power in the future. And that could be through hydropower, it could be through looking at cooling water for things like coal-fired plants or nuclear power plants and such. So we were able to do that for the entire western United States. So again, this is all scalable and doable. essentially with available information. And depending on where you're at, maybe you have as much information as we had available to us. We really had a lot of cooperation from the state, from the Western States Water Council. So we were able to pull together quite a bit of information. But depending on who you are, where you're working, and what your goals and needs are, you can pull together what's available and use it to the best of your ability. So in summary, the overall goal of IWRM is to improve our understanding of management and the governance of water resources by implementing a more holistic, systematic, and integrated system than was historically done, with the historical management approaches were. Again, we don't think that we're inventing something new. We've done a lot of good work in the past. This is just really saying we need to be more holistic, more systematic, more integrated than we have in the past. We're just trying to up the game a little bit. And we need to design a conceptual model to help us better visualize, plan, and monitor our resources and those issues and activities that affect them or are affected by them. Again, we need to be able to look and understand those, have a conceptual understanding of what those relations are between the various aspects. We need to capture, display, and link all the significant pieces and parts of the water management puzzle together in one place. And that allows us to ground a shared understanding of the hydrologically interconnected resources. So not just the people doing the study, but others who look at the studies and others who have to implement the study, or when we're just talking about implementing a program, everybody should be able to look at this and understand this interconnection of the resources. And by doing so, I think we can better frame our knowledge and better contemplate the whole integrated picture. And that'll allow us to improve the management and governance within our competent hydrologic units of interest. So that's really the big picture of where we're trying to get. So with that, I say thank you for your time and attention, and I look forward to hearing your questions or comments.
Great. Well, thank you so much, Jerry. You just covered a lot of ground and just great stuff. And I just love all the research that you brought to the table. So this is many years of work that you were showing us today, yes?
Yes, it is. We've been working at this for quite some time now.
So we got about 10 questions. I'm going to try to go through as many as I can given the amount of time we have left. But let's go ahead and start a little bit of discussion about the conceptual models itself, so the idea of a conceptual model. And someone was wondering, can a conceptual model accommodate changes in uncertainty, for example, things like climate change?
Oh, absolutely, yes. Conceptual model it should never be cast in stone. It should always be adjustable. It should always reflect what our knowledge is. Again, there'll be a lot of stuff we're asking people to look at a much bigger picture and to tie more things together. Well, a lot of those things we may have just a cursory amount of information on those. And from that, we know that in the future we may know more. We need to be able to bring that new information, new revelations, information from looking back historically even, and saying how well did we do and how do we manage different, or what's the other information we're finding out. So yes, it should be able to bring in stuff from relative to climate change or any other changes that happen.
Great. Well, here's another question about the conceptual model. So one of the things that the listener heard you talk about was the fact that a challenge for IWRM is the fact that there's a potential for too many programs, that people actually maybe throw too much into what we're trying to get done. And so they're wondering, how can you use a conceptual model to help address that kind of a problem?
Well, I think with the conceptual model, if we just wrote down all this information, all the things we're thinking about in black and white, in a Word document or whatever, often the things start getting lost. They start falling off the table, or we can start losing track of them. By building a conceptual model like we have here, what it allows us to do is see all those pieces and parts. And if you start looking and you say, oh, I just developed 101 different things I need to do next week, then maybe it'll allow you to say, maybe I need to back off on some of these, maybe prioritize or reduce the expectation of what I'm going to try to accomplish here. So I think that it allows us to visually look at things and understand the scope and the magnitude of what we're doing.
That's great. I had a professor years ago that said, if you can't draw it, you can't do it.
Oh, he's got to be a good friend of mine, my new professor, because he's very
Maybe,
always said that. Yeah.
yeah, mine was Dr. Deming, but maybe they had the same professor. So so one of the other things people are very interested in what you were talking about, how aquifers can transcend watershed boundaries, and the fact that it's not just a jurisdictional boundary, but you might have groundwater, you might have all these other kinds of things. So this particular person was wondering how you can take and do IWRM plans in these different jurisdictions without needing to have two plans. Is there some way to get them into one plan, even with these multiple jurisdictional concerns?
You know, you can do it, and in some cases we do it because we're cooperating with our neighbors and such, and some it's that we just have to do what we can. So if we think about it, a lot of aquifers, what we know, we all know from our basic hydrology is that aquifers and watersheds and basins don't match up perfectly. They often don't. So we're always going to have, or we're often going to have, mismatch between those two. And so what it may be is that portions of either, it could be the watershed or portions of the aquifer, one could be much larger than the other, and you could have multiple watersheds over a single aquifer, as we have on the Snake River Plain, or we could have multiple aquifers under a watershed, depending on how big of a system we're looking at. And what you need to do is look and say, within the scope of your study, where am I focusing on? And that's where you focus the majority of your efforts. But you also have to say, what other things are connected, and what information can I get to understand that? And how can I use that information to potentially manage water? And if it's a different jurisdiction, then you hopefully can negotiate with your neighbor and say, we need to work together on this, and hopefully they can. Well, historically, a lot of states haven't, especially on groundwater issues. And in certain cases, also surface water, right? We've had a lot of battles in the history of the West, especially over these. But what you have to do is you can always look up information that's not within your jurisdiction, maybe. And it may be that you get less information from publicly available resources on the internet or wherever, but you get that information to help inform. You know, whatever you have, get it to help inform. You try to enhance it with anything that your neighbors are willing to share with you, and hopefully that they're willing to cooperate relative to management. Not always the case that we can get to that last part, but hopefully we're getting better at that. So.
Mm-hmm. Mm-hmm. So I have a couple questions kind of about the context or the governance piece of this. So one of them is the our American Water Resources Association policy on IWRM really kind of talks about sustainability and integration. And the questioner is wondering, does this mean that you're managing more than water? It's not just integration of quality, quantity, surface, ground, but it's actually an interconnection of the community, the land use, the way energy's produced, the way food is produced, et cetera, in sustainability ways. I mean, does that integration definition reach into the bigger context?
Yes, absolutely it does. In fact, the definition of IWRM and all of the documents supporting it tell us it's bigger. It was actually the concern is that we may get too big. But what it says is just by the definition, at least we should be looking at the water and the land and the social and economic, right? It says that we should be looking at that bigger picture. And yeah, clearly it's not just about water. It's not just about water and land. It is all the other. It's ecological and it's social and it's economic. We need to look at all of these aspects and integrate them to the best of our ability.
Well, your answer triggers two of the other questions that we received. One of them is about how you can use the conceptual model to assist in comprehensive land use planning at the state and local government levels. And then the second thing, these are two separate questions, but the second one had to do is, can the tool help us speak to policymakers and the public so that we can transition water agencies from just looking at integrated water management as a project, but instead of that, it's just the way you do business. So I think those two questions kind of pair. What are your thoughts about that?
Yeah, I think the beauty of a conceptual model is that if it's done right, and if it's presented to people to where they can see the bigger picture, then they see where they lie in the entire universe of what you're studying and what you're trying to implement. And once they see what their place is, and they see that what they're doing is impacting you, and what you're doing is impacting them, or what they're doing can help you, or what you're doing can help them, I think that that visual allows people to look and say, I see where my role is. I see what I can do to hopefully help the situation. I think it's really important. Again, when we just write a Word document or something like that, I think these things get lost. People's eyes get a little blurry. They get tired of reading the tomes and maybe just kind of give up on it. I think when we make a good conceptual model and then describe it, I think it helps bring things to life and helps bring things to light to where people can understand how, their role and how things affect them and how they affect others.
Mm-hmm, mm-hmm. So again, you kind of this was phrased as a question, but I think it's more of a comment, which was, so when you're looking at water use and you're looking at use broadly, that really should be including things like fishing, bird watching, aesthetics, floodplain use, non-point pollution. So it's really a full portfolio that you're embracing. I'm going to go ahead. We're getting tight on time here, and I'm just so thrilled that we could do this today. This last question is kind of fun. Have you considered how the analysis or tool would look different if you analyzed opportunities as opposed to constraints? For instance, rather than the lack of public support being constraint, the attainment of public support being an opportunity. What would you, or how would you approach this in terms of what would a project look like, if the community really wanted this? So,
terminology is important, and it's important how we look at things. And I guess in reality, everything. What's the old Chinese saying about chaos and opportunity? Everything's an opportunity. Everything's a potential opportunity. Everything's a potential constraint. And I think it would be very helpful to look at both aspects. Every time we look at an issue or an aspect, I think if we look at both sides of that, what are the opportunities and what are the constraints, I think we would actually do a much better job at it.
Mm-hmm, mm-hmm. Well, that's great. Well, Jerry, once again, we just cannot thank you enough for your contributing to a little bit more of our understanding of IWRM today. Any last thoughts for our viewers?
No, I would just say let's continue marching forward, and everybody needs to add their piece in. As we're trying to improve water management in the United States and elsewhere around the world. We can learn by sharing with each other, and we can learn by looking at what each other's doing, and try to get the lessons learned on how to improve what we're doing and how we can reduce the problems. So
that's great. Well, thank you again. Have a great rest of your day, and thank you to everybody that's joined us in this presentation. Take care. Bye-bye.
Thank you.